Hi, I'm Monica Manises from Future Society, and today we will be tackling limits as part of CSMATH1. So for this video, you'll be tackling the following topics. So first, we will be tackling finding limits graphically and numerically. And then next, we will be evaluating limits analytically. So for this one, we'll only be covering some of the basics for this. So first, let's just say that the definitions and properties in this slides were adapted from the following book, which is The Calculus of a Single Variable, 10th edition by Ron Larson and Bruce Edwards. So let's get right into it and introduce what are limits. So there are two ways to define limits: the intuitive definition of limits and the formal definition of limits. So let's first take a look at the formal definition of limits. It's kind of confusing when you look at these statements with a bunch of numbers, and actually no, there aren't many numbers, it's just zeros, but mostly just symbols. So before we try to understand this, let's get into the intuitive definition of limits. So the intuitive definition of limits is just that suppose f of x is defined when x is near the number c. This means that f is defined on some open interval that contains c except possibly at c itself. Then we write the limit of f of x as x approaches c is equal to L if we can make the values of f of x arbitrarily close to L, as close as we like, by restricting x to be sufficiently close to c on either side of c, but not equal to c. So this just means that if we can try to get x as close to c as much as possible, then we can get f of x to be as close to L as much as possible. So going back to the formal definition of limits, so this just means, so f is a function on an open interval containing c, a constant, except possibly at c, and we let L be a real number. The statement, the limit of f of x as x approaches c equals L, just means that for each epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus c and is less than delta, then the absolute value of f of x minus L is less than epsilon. So this just means the same thing, but just formally. This just says that if we make c as close to x as possible, then we can get L as close to f of x as close to L as possible. So here, let's practice by taking a look at this graph below. So when x is approaching -5, what would be the limit of the function f of x? Here we will see that x -5 is over here. So if we go up here to the function, we see that the function approaches 4. So the answer for this would be 4. And then next, here, for -3, -3 is around here, and when we look at the function, this would be approaching 0.2. So that's how easy it is to find out the limit just by looking at the graph. Next, when x is -1, that would be around here, and since the function is approaching two different things at x is -1, so here on the left side we see that it's approaching -infinity, then here we see that it's approaching this is about 7. So since the left and right sides do not match, this would mean that the limit does not exist. And next, for number 4, as x approaches 0, the answer would be does not exist also, because from the left side the answer would be 0, but from the right side it would be -2. So the answer would also be does not exist. And next, for the limit of f of x as x approaches 2, that would be around here. Since once again, from the left side and the right side of the function, they're approaching different things. So it's here and it's here. So that's also D. Next, as x approaches 4, that would be here. And once again, since the left side is approaching positive infinity and this one is negative infinity, this would be does not exist. And next for 6, 6 is here. So if we check the function, this would be approaching 8 from both the left and the right side. So the answer would be 8. And then last, the limit as x approaches 8, 5, 6, 7, 8, this would be here. And it would be approaching, this is 1. So the answer would be 1. Next. Okay, so here is trying to get the limit by looking at the table of numbers. So here we can see that from the left side, f of x is approaching 2. See, it's 1.949, 1.995, 1.999. So this would be approaching 2. And same for the right side, it's going downwards, getting closer also to 2. So your answer for the first number would be 2. And then next, you just use the same logic for here. The answer would be negative 8. And then here the answer would be 3. Then here the answer would be negative 5.5. So if you need a minute, you can just pause this video before proceeding. Okay, next. So next we try to evaluate limits analytically. So it's time to use our brains more. So for this part, we'll just give the definition of some basic limits. So this says that the limit of b, a constant b, or a real number b, c, the limit of b as x approaches c would just be that real number b because it's constant. And then the limit of the function x, just x, as x approaches c would be c because this would be a linear function. Well, a lot of them will be linear functions. It would be the most basic linear function that's just going, yeah. So at every point here, the graph would be going to the constant, to the real number c. And then as well here, if you're given the limit of x raised to n as x approaches c, the answer would just be plugging c in as the value of x, which would give you c raised to n. And here we have more properties of limits. So we have the scalar, multiple, sum or difference, product, quotient, and power. And these are pretty intuitive. It's mostly just following also the rules of real numbers. So if you're given this limit and this limit, it just says, and you have real numbers b and c, the scalar multiple property says that if you multiply b to the function f of x, the limit of that new function as x approaches c would just be b times l, which is this one. So it would be b times l. That's what you get from l. And then similarly here, when you add or subtract two functions, the limit of that new function as x approaches c would just be the limit of would just be the sum or the difference of the limits of those two functions. So that would be L plus or minus K. And then same with product. You just multiply them this time, so LK. And then when with the quotient, you just divide them, provided of course that the limit of g of x as x approaches c, which is k, is not 0, because of course you can't have a denominator that's equal to 0. And lastly, the power property of limits. So if you have this, it's just L raised to n. Okay, so let's clear all of these. Is it possible to clear all of these? I'm not sure. Okay, let's just erase them. Okay, and now let's just try solving the examples on the right side. So if you have the limit of 3 as x approaches 2, this is your first rule here, which is just 3. And if you have this, the limit of x as x approaches -4, it would just be this one, which is -4. And then here, if you have this limit, it's just this rule here, so it would be 2 squared, which is 4. And lastly, this one is just, you can just substitute 2 to the equation inside, so this would be 4 times 2 squared plus 3, which is 4 times 4, 16 plus 3 equals 19. Okay, so here we have some more examples. So the rule on the right just says that if p is a polynomial function and c is a real number, then the limit of p of x as x approaches c is equal to p of c, which is what we did in the previous slide. And that is because of the rules of limits, the sum and product and the differences. Yeah. And here, if r is a rational function given by r of x equals p of x over q of x, and c is a real number such that q of c is not equal to 0, remember that this is just similar to the quotient rule in the previous slide. And there, we'll notice that the limit of r of x as x approaches c is just r of c. So you just substitute c into the function. Similar here, you just substitute c. Okay, then similarly here, again, if n is a positive integer and the limit below is valid for all c when n is odd. So if you have the nth root of x, you just substitute c here when n is even and c is greater than 0. And okay, last here, the limit of a composite function. So if f and g are functions such that the limit of g of x as x approaches c is equal to L, and the limit of f of x as x approaches L is f of L, then you can substitute their values here. So it's just like saying that if you have the limit of this composite function f of g of x, you can make it the composite function f of the limit of g of x, which then would just be f of L, because the limit of g of x as x approaches c is L. So if you substitute that here, it would just be f of L. Okay, so let's go on to the examples here on the left. So if you have this is a combination of this rule and this rule. So you can just substitute 2 here. You'll get 2 squared plus 3 times 2 plus 2 all over 2 plus 2, which is 4 plus 6 plus 2 over 4, which is 10 plus 2, 12 over 4, which is 3. And here again, you just substitute 5 in. This is going to give you the 4th root of 25 plus 50 plus 6, which is going to give you 75 plus 6, 81. So 4th root of 81, which is 3. And here we have, if the limit of f of x as x approaches 2 is equal to 5 and g of x equals x squared plus 5, we're asked to find the limit of the composite function g of f of x as x approaches 2. So here we can just make it as follows. So since g of x is a polynomial function and f of x is just 5, we can use this rule here below. So we can just make it g of limit of x approaches to f of x, which is going to be g of 5, which is 5 squared plus 5, which is 30. So that will be your answer here. Okay, then here I'll be giving examples on certain techniques that you can use to find the limits. So first is if your denominator would result in 0 when you substitute your c. So for example here, if you substitute 3, then if you substitute 3, you're gonna have a denominator of 3 minus 3 is 0, which we don't want to have. So in order to remove that, we would try the dividing out technique, which is if the numerator is factorable, we try to factor that out first and then divide that by the denominator. So let's do that. So if you factor out the numerator, this would be x minus 3 times x minus 2. Then all over x minus 3. So the dividing out technique is just that. You divide out what you can cancel out. So, and then you're going to be left with limit of x approaches 3, x minus 2, which would then be 3 minus 2 equals 1. And then another example of this would be here. If you try to substitute negative 1 here, it's going to be negative 1 plus 1 equals 0. So you don't want that. So we try to cancel it out again. So you factor out the numerator, which is going to give you x plus 1 times x minus 6 all over x plus 1. And then you can cancel out x plus 1, which is going to give you with, whoops, let's put negative sign there. Okay, so it's going to be limit of x approaches negative 1, x minus 6, which is going to be negative 1 minus 6, which is negative 7. And then here we have another technique we can use to find limits. So it's the rationalizing technique. So if you see limits that involve these type of questions, and then when you substitute the value here to the function, you'll have a numerator of 0. That's most likely when you'll be using the rationalizing technique. So this makes wise use of this property. So a plus b times a minus b equals a squared minus b squared, because when you do that, it's going to help you remove square roots in the function. So for example, you have a square root of a plus b times square root of a minus b. This is going to result in a minus b squared, so which is helpful for us. Okay, so I'll just demonstrate this out. So if you have the limit, this limit here, you'll multiply it with the inverse of the part that has the square root. So you'll multiply it by the root of x plus 1 plus 1 all over x plus 1 plus 1. So you're doing this because, you know, these two just cancel out, right? So you're not doing anything that's invalid. So yeah, and then when you do that, you can reduce the numerator to x plus 1 minus 1. So what happened there? It's just applying this rule, which is going to give you square root of x plus 1 squared minus 1 squared, which is x plus 1 minus 1. And then your denominator would then be x times root of x plus 1 plus 1. This is going to give you, let me erase here. Okay, so this is going to give you limit as x approaches 0. It's going to be x over x times root of x plus 1 plus 1. So here you can divide out x using the technique above. So you divide that out and you'll be left with, okay, I'll just write this here, equals limit of, whoops, limit as x approaches 0, 1 over root of x plus 1 plus 1. Then when you substitute 0, you're going to get 1 over 1 plus 1, which is 1/2. So if you don't believe me, you can pause this video and try to analyze that. And then next, let's go here. So for this number, we'll have the limit of as x approaches 16. So when you try to substitute 16 here to the function, you'll get a denominator of 0, because 16 minus 16 equals 0. So what you want to do is again rationalize. So multiply it by the inverse. 4 minus root of x over x minus 16. So what would you multiply this by? You multiply it by 4 plus root of x, because you want to be able to remove that square. Over here, you'd also have that. And then this is going to give you, oops. Okay, so this will be 16 minus x. How did that happen? Again, just doing some magic here. Root of x equals 4 squared minus root of x squared, which is 16 minus x. Right? So there. And then the denominator will be x minus 16 and 4 plus root of x. So if you notice, this one and this one can be cancelled, leaving you with negative 1 up top. So this will be limit of x approaching 16, negative 1 over 4 plus root of x. And then the answer here, when you substitute 16, would then be negative 1 over 8. So then that's going to be your answer. Okay, so for this slide, let's just do a couple of more questions to solve limits analytically. So let's start. Okay, so for this first one, let's just check first. Maybe substituting it would work. So here, let's try substituting x equals 0. So this will give you 0 squared is 0, minus 25 all over 0 squared is again 0, minus 4 times 0, which is 0, minus 5. So this will give you negative 25 over negative 5, which is 5. So the answer for this first question would then be 5. Okay. Next, let's proceed to the next question over here. So for this one, if we try substituting 5, we'll end up with 5 squared, which is 25, minus 25, all over again 5 squared, which is 25, minus 4 times 5, which is 20, minus 5. So this will give you 0 over 0. So this is when we can apply the techniques that we taught a while ago. So in order to do that, we can take a look at our question here, and we can notice that maybe we can factor out the numerator and the denominator. So let's do that first. So x squared minus 25, you'll notice that this is x minus 5 times x plus 5. And for our denominator, x squared minus 4x minus 5, this is equivalent to x minus 5 times x plus 1. So this limit would then be limit as x approaches 5, x minus 5 times x plus 5 all over x minus 5 times x plus 1. And with this, we can divide out x minus 5, leaving us with x plus 5 over x plus 1. And we can substitute 5 there, so we'll have 5 plus 5 over 5 plus 1, which is 10 over 6, giving us 5 over 3. So our answer for this question is 5 over 3. Okay, and then here on this left side, let's proceed with the next number. So for this one, if we substitute 1, we'll get 7 minus 4 minus 3 all over 3 minus 4 plus 1, which again is 0 over 0. So using the techniques a while ago, again, we can try factoring this out. So 7x squared minus 4x minus 3, this is going to be equivalent to x minus 1 times 7x minus 3. And the denominator, 3x squared minus 4x plus 1, this is going to be x minus 1 multiplied by 3x minus 1. Okay, so when we rewrite this limit, it will become limit as x approaches 1, x minus 1 times 7x minus 3 over x minus 1 times 3x minus 1. So we can divide out x minus 1, leaving us with 7x minus 3 over 3x minus 1, and substituting 1, we have 7 minus 3 all over 3 minus 1, which gives us 4 over 2. The answer for this would then be 2. The answer here is 2. Okay, so let's erase the solutions on the right side so we can proceed with the next number. Okay, so here, for this one, let's try substituting -2 again. Over on top, we'll get 16 minus 40, because 5 times -8 is 40, so minus 40 plus 24 all over. So -2 squared is 4. 4 times -2 plus 1 is -1. And we have minus 4 times -1. So with this, once again, we'll have 0 over 0. So we will have to do our techniques from a while ago. So for this, we can try factoring out the numerator and the denominator. So for the numerator, we have x raised to 4 plus 5x cubed plus 6x squared. So this will give us x squared times x squared plus 5x plus 6. And we can further factor this out to x squared times x plus 2 times x plus 3. Okay, and as for the denominator, I'll write that down here below. So x squared times x plus 1 minus 4 times x plus 1. So if you notice, we have x plus 1s here, so we can factor that out. And that's going to be x plus 1 times x squared minus 4. X squared minus 4. And we can further factor this out to x plus 1 times x plus 2, x minus 2. So then we can rewrite this limit as, I don't know if we'll have the space, but let's try. Well, it'll be x squared times x plus 2 times x plus 3 all over x plus 1 times x plus 2 times x minus 2. So we can cancel out here x plus 2, x plus 2. And when we substitute -2, we'll have -2 squared times -2 plus 3 all over -2 plus 1, -2 minus 2. And this is going to be 4 times 1 all over -1 times -4, which will give us the answer of 1. So the answer for this question will then be 1. So for now, I'll just erase the previous solution on the left side so that we can proceed with that. And for this one, I'll start writing with red so that we can differentiate it with the other scribblings around there. Okay, so here, if you try substituting 3, you'll get 3 squared minus 9, which is 0, as your denominator. So we know that we'll have to substitute the techniques. And here, so what we'll have to do is rationalize since we have a square. So let's write that up top here. So limit x3 square root of x plus 1 minus 2 over x squared minus 9. So you'll multiply it by the inverse of the part with the square. So you multiply it by root of x plus 1 plus 2 all over root of x plus 1 still with plus 2. And then this is going to give us limit as x approaches 3, x plus 1 minus 4 all over, this is x squared minus 9 times the root of x plus 1 plus 2. So if you're wondering how the thing up top happened, again, it's because of a plus b, a minus b. So it's equals a squared minus b squared. So you'll be having square root of x plus 1 squared minus 2 squared, which is how this happened. Okay, and then from here we'll have limit as x approaches 3, x minus 3 all over So you can factor out x squared minus 9, x minus 3 times x plus 3 times the whole root of x plus 1 plus 2. So it's getting kind of messy, so just put it down there. And then we can factor out x minus 3 and x minus 3. So we kind of combine rationalizing with dividing out here. And then here we'll have limit as x approaches 3, and your numerator will become 1 all over x plus 3 times square root of x plus 1 plus 2. And then when you substitute 3, you'll have 1 over 6 times square root of 4 plus 2, which is square root of 4 plus 2 is 4. So this will give you 1 over 24. So your answer here is 1 over 24. Okay, and now I'll proceed with deleting the black parts of our solution so that we can make space for new parts of our solution. Okay. Okay, so for this, maybe I want to use purple. Okay, so for this one, if you try to substitute 2, you'll get square root of 4 plus 5, which is 9, which will be 3, minus 2 plus 1. So this will give you 0 still, because that's 3 minus 3 plus 0. So again, we'll have to use one of our techniques, and since we have a square root, we can do rationalization. So for this one, okay, so I'll start here up top again. So let's go limit as x approaches 2, x squared plus 2x minus 8. So for this one, you can actually factor out x squared plus 2x minus 8 into x minus 2 times x plus 4. Then you can just copy the denominator. So x squared, root of x squared plus 5 minus x plus 1. And then we'll multiply it by the inverse of the part with the root. So it's going to be root of x squared plus 5 plus x plus 1 all over root of x squared plus 5 plus x plus 1. Okay, so with this, I don't want to copy the numerator just yet, just because it's so messy. So let's proceed with multiplying the denominator. So let's do that down here. So again, that's going to be square root of x squared plus 5 squared minus x plus 1 squared. And this is going to give you x squared plus 5 minus, and then this part is going to follow the rule that is a plus b squared equals a squared plus 2ab plus b squared. So if we do that, this is going to be x squared plus 2x plus 1. And then here, this will then become just negative 2x plus 4. So we'll cancel out the x squared and the x squared. There. Okay, and negative 2x plus 4, this is just negative 2 times x minus 2. So, so that we don't have to copy the whole thing, we can just cancel out x minus 2 and x minus 2 here on already. And then we'll be left with equals lim x to 2. So it's going to be x plus 4, and then square root of x squared plus 5 plus x plus 1 all over negative 2. So when we substitute 2, this is going to be 2 plus 4 is 6. So 6 over 6 multiplied by square root of 2 squared is 4 plus 5 is 9. So that's 3 plus 3 plus 2 plus 1 all over negative 2, which is going to give us 6 times 6 over negative 2. So this is going to be negative 18. So that would be our answer right about here. Okay. So for this next part, this is just kind of a brain teaser. See, there's no numbers involved. So we'll see how messy this gets. Okay, so for this one, let's try to dissect this. So it's saying that the limit of f of x as x approaches a is L, and the limit of g of x as x approaches a is I. The limit of h of x as x approaches I is y. The limit of f of x as x approaches b is a. So for this, you have 3 composite functions multiplied together. So, well, we can dissect this into 3 different limits so that we don't give ourselves that hard of a time. And for that one, I'll assign them different colors. So this one should be green, and I'll give this one dark blue, and then this one is dark red. Okay, so for the green, this would then be limit of x to b multiplied, the limit of g of f of x. Okay, so for this one, the answer would be, first we get the limit of x to b in f of x, which would be a. So then this would be limit of x to a g of x, which would then give us I. So that's one of our answers. Okay, and then next, we'll do the blue part. So this will then be limit of x to b f of x. So this part, the inside part, again, we know that this is a. So it's going to be limit of x to a of f of x, which is going to give us L. And then last, for the red part, it's going to be limit as x approaches b and h g f of x. Okay, so for this part, we'll start with the innermost part, which is limit of f of x as x approaches b, which is, again, as stated a while ago, it's a. So this is going to be limit as x approaches a of h of g of x. And then x approaches a and g of x, this will give you I. So then this is going to be limit of x approaching I, h of x. Then this will then be y over here. So your answer is y. So the answer for this question would then be I, L, Y. So I guess if you wanted to convince with your CSMATH1 classmate, this is the way to both rack their brains with limits and also low-key confess. Okay, but don't try to do that. I mean, you can try to do that, but at your own risk. Okay, so I think that's all for our review session for today. And I'll just give a slide with some more review questions that you can try to solve on your own. So for some more questions for your extra practice, here are some questions that, for me, they're a bit tricky, but it's a good way to practice finding them. You can take a screenshot of this before I go to the next slide, because on the next slide there will be answers. So 5, 4, 3, 2, 1. Here are the answers for these questions. So here are the answers to the questions, and I think that's about it. Thank you for watching this video, and once again, I'm Monica Malices from Peer Tutor Society, and thank you for trying to learn more about them.